Hello everyone. I want to share with you a simulation model of a signalized intersection where you can customize every aspect of the intersection you're analyzing. For sure, there are ready-made simulation softwares that provide powerful capabilities for modeling complex intersections and networks. However, these softwares typically assume standard and ideal driving situations. So if we have non-standard situation, for example, car arrivals that does not follow a random Poisson distribution, which is typically embedded in these ready-made softwares, it would be a little bit tricky to configure these softwares to capture the specific situation that we are having. This is a discrete event simulation model that could be used as a supplementary analysis tool for such cases. Before I go through the model itself, perhaps it's a good idea to have a look onto the intersection, the layout of the intersection we're about to discuss. This is a Yonge and King intersection at downtown Toronto, and it's a simple four-leg intersection, and obviously the left turn movement is not allowed in this particular intersection. And let's go and run the model. Let us slow it down a little bit and run. It's a two-phase signalized intersection. Right now the right of way is given to the north-south direction. At the left of the screen there are 8 creation modules. Each one of them represents a particular movement. The upper left, for example, is for the northbound through movement, and then below it there's the northbound right movement, and then southbound through, and so on. Each of these creation modules allows you to input the specific arrival rates and arrival distributions related to the particular movement we are inputting. At the middle of the screen we are having sub-model for crossing the intersection. Let us have a look here. Let's close the sub-model. Next we're having a decision module that figures out where every vehicle final destination would be. And finally we're having a dispose module which counts the number of vehicles that arrives at every destination. So there's a number of issues going under the hood. However, I want to focus on the queue formation and queue dissipation. The queue formation is related to the arrival rates and arrival distribution that we input, but it's a little bit tricky when we come to the queue dissipation. I have linked the saturation flow rates to the queue dissipation in this particular model, and in this for this intersection, for example, I have used the saturation flow rates recommended by the Canadian Capacity Guides for Toronto downtown intersections. And let's run the model a little bit faster so we can have a look on the results and the final report. Yes, we want to see the results, please. We are interested in the queues. The main performance measure here is the average wait time that vehicle faces while queuing. So here we have 4 queues and the average waiting time in every queue of them, and it's almost 13 seconds. A little bit higher for the westbound queue, around 15 seconds, which is a very good level of service here. I have validated these numbers with a standard HCM procedure for calculating the average delay, and I have arrived at very comparable numbers within plus or minus 1 second. So the model is valid in this sense. And that's it, and I hope you find this video useful, and bye for now.